Okay, so now that we've talked about covalent compounds and how these elements bond, let's talk about how these shapes are actually formed. And this is VSEPR theory. And VSEPR stands for valence shell electron pair repulsion. So the name is telling you what is actually going on here. So it's the valence shell electrons that are already paired up are going to be repelling the bonds. So you need to keep in mind that everything wants to be as far away from everyone else as it possibly can. So this VSEPR theory is going to determine the molecular shape of a compound. So these valence shell electrons repelling these bonds are going to give us our shapes. So it's going to be dependent on the number and placement of your non-bonded or your unshared pairs of electrons. Those are the valence electrons that automatically pair up when we draw our Lewis structures. So these non-bonded electrons are going to repel all of the bonds, and that's going to affect the shape of our molecule. Remember, our goal is to create an octet or fill your valence shell. Remember, the atom with the most free valence electrons will usually go in the middle. That's going to be our central atom. So if we look at a linear molecule, linear means it's going to be a line. It's usually going to have 1 to 2 bonds, and it's going to make a straight line. It's linear. So if we look at hydrochloric acid, okay, hydrogen has 1 valence electron, chlorine has 7. One of them are free, so these 2 free valence electrons are going to come together and bond. That means we have 1 bond between the hydrogen and the chlorine. And so you can see that this shape here makes a line. It is linear. You don't draw the blue line through it when you're actually answering, but HCl is linear. There's a straight line there. You can have 2 bonds, so another example would be carbon dioxide. So CO2, you would have carbon in the middle, with 2 double bonds going to each oxygen. You can see there that it is a straight line. It is linear. So normally you're either not going to have a central atom, like in the hydrochloric acid case, there's no central atom there. Or if you do have a central atom, there's not going to be any unshared pairs on it. So it's going to be all by itself like this. The next shape is bent or angular. And so that's going to have a central atom. It's going to have 2 bonds and 2 unshared pairs hanging off of that central atom. And so if we take water for our example, we have 2 hydrogen. Each hydrogen has 1 valence electron. We have 1 oxygen, which has 6 valence electrons. So that leaves room for each hydrogen to attach to the free electrons on the oxygen. So we're going to put oxygen as our central atom. You're going to have 2 bonds hanging off, 2 unshared pairs. It's going to help you see the shape if you put like things next to each other. So if we put these 2 unshared pairs next to each other and the 2 bonds next to each other, you can kind of see its shape there. So this is hydrogen and hydrogen. So what's happening is these electrons are actually taking up quite a bit of space. And so they're going to push these bonds down and away so that you get this bent shape here. So it looks kind of like an L. It's been bent. There's an angle there. Next is trigonal planar. We know that tri means 3, so there's going to be 3 bonds here. And planar, it's going to be flat. Okay, it's all in the same plane. So central atom will have 3 bonds and no unshared pairs. So you're not going to be bending one way or the other. They're going to spread out as far away from each other as they can. So if we have BH3, boron has 3 valence electrons. We have 3 hydrogens. Each one has 1 valence electron. So 1 free electron from each boron, or from the boron, is going to pair up with each hydrogen. We're going to put the central atom, that's going to be boron. And now to make each bond as far away from each other as possible, this one's going to form kind of a Y shape, so that you have each hydrogen here. So you're going to want these bonds as equal distance as you can away from each other. In real life they are at equal distance, so just draw it the best you can. It'll be in a Y shape. There's no unshared pairs here to push them one direction or another, so they're just going to spread out as far away from each other as they can. Next is the trigonal pyramidal. So again, we have 3, but now we have this pyramidal shape. And so what's going to happen is your central atom is going to have 3 bonds, and it's going to have 1 unshared pair hanging off of it. So if we look at NH3, which is ammonia, we're going to take our nitrogen, which has 5 valence electrons, and we have 3 hydrogens, each one with 1 valence electron. So those 3 free electrons on the nitrogen, each one's going to pair up with a hydrogen. And so now you have this lone pair here. Okay, so these 3 bonds are still going to try and be as far away from each other as they can. Remember, these electrons are going to take up extra space. So you're going to have your nitrogen in the middle. You have your lone pair up here at the top. These hydrogens are going to push down and away. Okay, so this guy, he might be kind of pointed back, so we can give him like an open triangle. And this guy might be facing forward, so we can give him like a closed triangle just to represent our 3-dimensional image here. I'll show you a 3-dimensional molecule tomorrow. So these lone pair electrons here, they're pushing these guys down, okay, so that they're still making a Y shape like this, if you were to look at it from the top, but when you rotate it from the side, now you have this lone pair up here, and then it's kind of this pyramidal shape that's forming. Alright, last shape is tetrahedral, and we know tetra is 4, so this one's going to have 4 bonds. No unshared pairs. The most anyone can hold for this class is 4 bonds. So your central atom is going to have 4 bonds and no unshared pairs. So if we look at CH4, which we know is methane, carbon has 4 valence electrons. We have 4 hydrogens. Each one has 1 valence electron. So each free valence electron on the carbon is going to come over, bond to the hydrogen. So we're going to put our central atom in the middle, and then you're going to spread your 4 out the best you can. And so you can draw it like this. This is acceptable. But the 3-dimensional structure of it is going to look more like this. So it's very similar to the trigonal pyramidal. This guy will be going back, this guy is coming forward, and then these two would be in the same plane. So if you were to look down on it, you would have a hydrogen here on top, the carbon would be underneath of it, and then you'd have 1, 2, 3 hydrogens sticking out there.